In this video, I'm going to concentrate on centripetal acceleration, acceleration of an object due to circular motion. A very basic question. Is uniform circular motion accelerated? When I say uniform circular motion, I mean the object has constant speed. Is it accelerated or not? Let's check it. At this point, let's say it's the moment of t1. The object has a velocity like v1, a vector tangent to the trajectory, tangent to the circle. At another moment like t2, the object will have another vector like v2. v2 is the velocity of the object at this moment. v2, although it has the same magnitude as v1 because the speed is constant, but it's a different vector, so necessarily it's accelerated. How to find that acceleration? You remember average acceleration was delta v over delta t. So first of all, I need delta v. Let's transfer v2 to this point. Now the two vectors are starting from the same tail, common tail. And then I will connect the end of v1 to the end of v2. A downward vector, but necessarily towards the center. So it is delta v. Now acceleration, average acceleration is going to be delta v over delta t, a vector toward the center. What about instantaneous acceleration? Instant means a very small, short time interval. So delta t should tend to zero. Actually, it approaches zero. How to find it? If I make the time interval to be very short, actually these 2 points are going to be closer to each other. For every arbitrary couple of points like A and B, they will have a midpoint, and using the same approach, I will find the same downward acceleration toward the center. If I take the delta t to be shorter and shorter, they are going to be closer and closer to each other. If delta t approaches zero, I cannot distinguish the 2 points. They merge. Anyway, still the acceleration is downward toward the center. So even instantaneous acceleration is toward the center. This is called centripetal acceleration. How to find it? Let's find acceleration. First of all, I make a copy of this shape here, and these are the radii at the points A and B. Here again is A and B, similar. Let's say this is the displacement, delta r. Displacement is going to be a vector connecting A to B. Okay. Here in this isosceles triangle, the legs are making a vertex angle of theta. Necessarily this is a theta, and also here we have the same angle, similar angle, theta. Why? Because here v2 is normal to the radius, and v1 also is perpendicular to the radius. So v1 and v2, the legs of this isosceles triangle, 1 to 1, are normal to r and r. So they will make the same angle, theta. By similarity of this triangle and this triangle, I can write the ratios of base and leg. Base over leg in velocity triangle is base over leg in radius triangle. And so I will rearrange the equation like that. Delta v is equal to v divided by r times delta r. Moving from A to B takes a time of delta t. Let's divide both sides of this equation by delta t. So I will have delta v over delta t, and here delta r over delta t. You remember the concept of moment is when delta t approaches zero. So let's take a limit when delta t approaches zero. Limit of delta v over delta t when delta t approaches zero is indicating acceleration. V over r is a constant because the speed is constant, radius of the circle is constant. And I keep limit of delta r over delta t when delta t tends to zero here. This limit indicates velocity, or let's say a speed. The magnitude is a speed. Speed is delta r over delta t. At the moment, it's instantaneous speed. So I have a v. If I multiply this v by this v, it will be v squared. So it's going to be v squared divided by r. This is called centripetal acceleration. The square of the speed divided by the radius of the circle. The centripetal acceleration is directed toward the center, as I mentioned. The acceleration is always at 90 degrees to the velocity vector. Why? Because velocity is always tangent to the trajectory, tangent to the circle, and acceleration is directed to the center. So it's aligned with the radius. So AC must be always perpendicular to velocity, normal. In every other point, you will have the same situation. Keep in mind. Acceleration, centripetal acceleration, as I mentioned, is going to be v squared over r in magnitude. If I substitute v by r omega, here I will have r squared omega squared divided by r. And so r omega squared. This is another version of centripetal acceleration if you want. And you remember v was r omega. So let's disintegrate this relation to r omega omega. And then here r omega is going to be v. So it's also v omega. So we have three versions for centripetal acceleration. As you wish, you can use one of them to solve the problems. It depends on the case. Let's solve this problem. An object is revolving a circle with constant speed, so it's uniform circular motion. Can we say this object has constant acceleration? Why? Guys, look, here I have acceleration, which is going to be v squared over r. Immediately you say, okay, constant speed, so this is constant, so acceleration is constant. But it is totally wrong. I will tell you why. Look, acceleration, rather than magnitude, it also has direction. It's a vector. This acceleration has a different direction from the other one. So it is not going to be constant. Be very careful. Acceleration has constant magnitude but changing direction. So it is not constant acceleration motion. Keep in mind, it's very important. The International Space Station, ISS, moves in an approximately circular orbit, 420 kilometers above the Earth's surface, with a linear speed of 7,650 meters per second. The radius of the Earth is given like that. Calculate the centripetal acceleration. To find the centripetal acceleration, as velocity is given, I can easily use AC equals v squared divided by r. And here v is going to be 7,650 meters per second. It is in SI units. And here in downstairs, be very careful. Here we have the radius of the Earth, and here we have the altitude. The radius of the ISS is going to be radius of the Earth added by the altitude. So it's RE plus the altitude. So in the parentheses, you see the total, the addition of these two values. On the other hand, I should multiply it by 10 to 3. The reason, downstairs must be also in SI units. So 10 to 3 to convert kilometer to meter. That's all. The answer will be 8.6 meter per second squared. This is the centripetal acceleration of the ISS. You remember gravitational acceleration is 9.81 almost. And it's smaller than that. The reason is altitude. The more you get further away from the center of the Earth, the less the gravitational effect. So acceleration is smaller. I mentioned gravitational acceleration. Yes. International Space Station or every other satellite is acted by centripetal force of gravity. So necessarily this acceleration corresponding to that centripetal force must be smaller. And it's the gravitational acceleration at that specific altitude. In the upcoming videos, I will tell you what do we mean by centripetal force. A cyclist rides along a circular track of radius 25 meters and at a constant linear speed of 30 kilometers per hour. Calculate the angular speed of the cyclist and the centripetal acceleration. First of all, let's go over angular speed. You remember linear speed and angular speed are connected like v equals r omega. I know the r is given here. I know the linear speed is given here. Of course, it must be converted to SI units. And I will find omega. Let's plug in the values. Here I have the velocity, the speed, and I've converted that to meter per second by dividing that by 3.6. So it's the speed in meter per second. Right side, I have the radius multiplied by omega. So easily you can find the omega to be 0.33 radians per second. Now, centripetal acceleration. It's very proper to use r omega squared. I know the r is 25 meters and I have found omega here. I plug in the values and then centripetal acceleration is going to be 2.8 meter per second squared. Thank you for watching this video and thank you for your attention. See you.